All right, when we start section 5.1, we're going to be looking at answering the question of whether or not a collection of data fits the model of a linear function. Now, the easiest way to tell for sure is to check a graph of it. So let's say there's an axis there, and I've got a couple of functions on it. So let's do one in blue to talk about. So here is a blue graph. There it is. Rid of that extra padiddle. So there's one. And then let's say maybe I've got another one that's going to look like, oh, keep it in blue. Let's say it looks like that. Oops. There we go. So there's another function. Now, when we talk about what a linear function is, we're talking about this guy. Visually, a linear function should follow the shape of a line, whereas a nonlinear is not. If the graph has a curve to it, then visually we can identify it as being a non-linear function. Now, of course, we also need to be sure, are we even talking about a function? So if I were to talk about, say, this graph, let's do it in red, which is a nice, neat vertical line. Because it's not a function, we aren't even going to say that it's a linear function. So if you think of it in another sense, we have this group. Those are all the functions. Inside that group, we have what are called linear functions. In this case, the red line that runs vertically, because it fails the vertical line test, the vertical line will intersect it more than once, is not even a function. So we don't give it the label of linear function. Yes, it's a line, but it's a special case of a line that's not a linear function because it's not in the function group. Now recall, a function is a relation where for every x value, so every item in my domain, every independent variable, there is exactly one output, one y, one dependent variable. So the two blue graphs that are shown here are both examples of functions. The difference is the one that has the curve to it is a nonlinear function. Now, once you've got the idea of the visual down, we can start to talk about some other ways of testing them. So, for example, let's look at some data and see if we can see a pattern. I'll use a linear function as our lead-in. So I'll go ahead and I'll make a little table up here. So here's my t-table. And let's put some numbers on my t-table. Here's my x, here's my y. And let's start with some simple numbers. 0, 1, 2, 3, 4. And over here I'll do 5, 7, 9, 11, and 13. Now, one thing I could do as a way of checking to see whether or not this is a linear function is I could graph it. And I could look to see, do I get a line when I'm done? So 0, 5 would be right here. Let's say that's 10 up there. And then 1, 7, 2, 9, 3, 11, 4, 13. And then I can check, can I draw a single line through that? Yeah, that seems to follow the path of a line. So the graph looks like it's going to make for a linear function. Now, there's another way we can check this without having to graph. What I'm going to do is I'm going to look to make sure that each of these is increasing by just 1. If it's increasing by other numbers, I can't use this method. So when I look, I can see +1. So each of these is going up by an even increment of +1. So now I can come over here and I can check these. Do they go up by even amounts? Well, 5 to 7 plus 2, 7 to 9 plus 2, 9 to 11 plus 2, 11 to 13 plus 2. I can see that the dependent variable, remember that term, the y values, dependent variable, or the y's, are increasing by a constant amount. That constant amount indicates that I'm looking at a linear function. It's the idea of saying that for every 1 I go over, I go up 2. Over 1, up 2. Over 1, up 2. Over 1, up 2. That constant up 2 is what establishes that I'm looking at a linear relationship. So I can go ahead and label this a linear function. Now, what might it look like if it's not a linear function in this context? So let's take another example. Let's say I have a collection of ordered pairs. So first I'll write it as a collection of ordered pairs in order to help organize what I'm going to do. I have 0, 2. I have 1, 4. I have 2, 6. And I have 3, and that's going to be 18. No, that's not what I want to do. Let's see. 3, 11. Okay, and then I'll do my curly bracket. Okay, so there I have a set of ordered pairs. Now, before I go any further, I want to put those onto a t-table. So this is what the problem will say. Here are some ordered pairs, and it will ask, does this represent a linear function? And that's my challenge. Identify if those do or do not. So first I'm going to put them onto a t-table. So I'll make my little t-table. Let's see, x, y, gets back to my black pen, a little easier to read. So 0, 2, 1, 4, 2, 6, 3, 11. Now let's check. These are all going up by increments of +1. That's a good sign. Now let's check. That goes up by +2. That goes up by +2. Oh, +5. That doesn't work now. So that's a sign that what I'm looking at is not going to be a linear function. This +5 means that it's not going to follow that nice steady path anymore. And I can go ahead and reject this data as a linear function. So to review what we've said so far, a linear function is going to have a constant increase as I work my way down the table. Compared to that, a nonlinear function is not going to have that constant increase. Now, I can still say that it is a function. Every value in the x column is being used exactly once in the y column. So it still fits the idea of function. It's just not linear, so I can't count it. In addition, we can also talk about what they should look like in equation form. Now, a linear function is a function I can write in this format. Now, a few things I want to say about that. Here's one that maybe has some numbers. 3x plus 2y equals 10. Or I might write 1/3 x plus y equals -2. Or 6x minus 5y is equal to pi. Or pi is 3.14, blah, 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 blah. All of these are examples of linear functions. Anytime I can take an equation and rewrite it so it fits this format, it gets slapped with the label of linear function. Anytime I find one that works out to follow that pattern, so if I go back, for example, to these problems, if you look down the column, I can probably write an equation that will fit that format that also fits this particular set of data. And that's the important part of it. Now, what I'm going to do is I'm going to use the equation that fits this model. You can see I started at 5 as my initial value at 0. I went up by 2 with each step, so that means my slope will be 2. So I want to write my equation out in y equals mx plus b form. So I might write out y equals 2x plus 5. Now comes the question, can I write this equation to be in the format like this? Can I rewrite it so that it fits ax plus by equals c? So what I'll do here is I'll subtract 2x from both sides of the equation, leaving me negative 2x plus y is equal to 5. Now I can see that what I've written matches more or less, there we go, more or less matches the equation above. What I've got here is an ax, negative 2 times x, plus by, 1y, equals 5. So that does represent a linear function. Now in contrast, I may have been handed this equation, xy plus y equals 10. Now this does not fit the linear format. No matter how I manipulate this equation, because I have the x and the y times each other, I can't combine them or move them around or do anything like that. I'm very limited in what I can get away with. As a general rule, the other thing you want to look for is an equation that you can write in this format, y equals mx plus b. Now that's often called slope-intercept form. That's a style of equation writing we're going to use a lot in here because it has an easy way of creating an equation from a story problem. It has the rate of change and the initial value. And you'll see many story problems fit that format, where they give you a slope and they give you an intercept. As we move more through the unit, we'll talk more about these two equations. So as a point of clarity, I'll put this guy down here so I can label them. This is what we call standard form. And this is what we call slope-intercept form. If I can write an equation in standard form, I can write it in slope-intercept, and then that represents an equation that is a linear relationship.